Hi, we are in this module on nature of materials. This is the second lecture in which we will be looking at lattice structure and defects. So, as you can see on screen, the electron configuration, bonding, etc. were covered in the previous lecture, and today we are going to talk about lattice structure and some of the defects in the materials. Okay. Now, these are some of the books which I used, as I keep telling, Mamlok and Zanussi, Callister, Ilsen and Domone's book. So, all these books and a lot of information from the internet have been used for making this module. Now, classification of materials can be done based on chemical bonds. For example, as you see here, the three major type of bond: metallic bond, covalent and ionic bond, and also covalent bonds alone. So, in the metallic bonds, of course, metals and the typical metals which we use in construction: steel, iron, aluminum, copper, etc. Okay. And also covalent and ionic bonds, they are mainly present in most of the inorganic or non-metallic solids like ceramics, and concrete is one very good example of ceramic material, bricks, glass, aggregates, all this. So, there in these you can see crystalline structure mostly, and then there are other type of materials which are mainly organic solids, where examples are asphalt, plastic, wood, etc., where we see random molecular structure. Again, one more thing I want to tell, even though we said crystalline structure, it is not that they are very well crystallized in nature, but more or less in general we can say they are crystalline in nature. Okay. Now, let us look at the metallic material, which is the focus on today's lecture now on, and then we will go into non-metallic materials later in the future lectures. So, in the metallic material, first let us see the process of solidification. How do we make metals? We get the raw materials, or raw materials for making the metal, and then we melt them. So, increase the temperature so high so that the material melts, and then we allow that material to cool down. So, in this cooling process, the solidification happens in the way we want. So, that is what is the engineering, metallurgical engineering plays a big role in that. So, one important thing to note is most of the metallic bonds are non-directional in nature. Why it is happening is because the crystal growth, when it happens, or when the molten material is cooled down, or when the temperature comes down, what happens is crystal starts forming. Okay. And depending on the rate at which it is cooled, the way in which the crystals grow also matter. Okay. Or the size of the crystals, or the grains, which we will call later on, we will talk more detail about that. So, these grains are formed, the size and the size of the grains and the imperfections and many things inside the metal in the 3D space, that is heavily dependent on the rate of cooling and the temperature which we adopt, etc. Rate of cooling mainly. Now, what happens here is an example of titanium crystal bar. You can see it is a lot of crystals on this. These are all individual individually grown crystals, you can see there, and you can see the nature is different in the center of this thing, and as you go away from the center, like over here, it is slightly different. Next slide I will show you more detail on that. Now, here you can see how the cooling rate matters. Okay. So, the top picture on this slide is the cross section of an ingot, okay, or we can call it a rod, and on the bottom you are seeing the side face, or the cross section in the longitudinal face is what you are seeing in the bottom. Okay. So, if I am talking like this, something like this. So, this bottom portion, this much is shown here and this is shown here, or any cross section for that matter is shown on the top image, and the bottom is shown in the bottom image. Now, the image is it's collected from the literature. So, this says nickel copper alloy, but it is not necessarily that one. I am just using this as an example. Now, effect of cooling rate and effect of impurities in case of alloys. Okay. So, what this does is, because of this temperature changes happening, there is a possibility of segregation between the elements present in the molten material. Okay. And also that will induce some change in the grain size and shape also. Okay. So, example is here, you can see the top picture, the cross section, when we look at this portion here, when we look at, you can see that near the surface it is actually very fine grain there. Okay. And then you have some region towards the center where you have elongated grains. Okay. And then towards the center you have again equiaxed or grains where the axis in both directions are more or less similar in size. Okay. Columnar grain, small equiax grain, so small equiax grain along the border, columnar grain in between, and then towards the center you have large equiaxed grains. So, here you can see very fine grains. Small equiax grain means very fine grains. The size of the grain is very small, and large equiax grain means the size is larger, but more or less similar size in all the directions. So, that is what equiaxed means. Okay. Now, same thing, although these two images are from two different literature, I thought it is good to show them together. As you can see, the same, kind of, you can see this is what is happening. So, the side view, how it would look. Now, here the important thing is, at the bottom also you have similar, because the material, if it is a rod, it is cooling from all the surfaces, not only the circular surface, but also from the bottom surface it is cooling, and that is why you see this kind of distribution of the grains. So, the point is, near surface of the metal might have a different grain structure. As you go in little bit inward, you might have another grain structure. As you go a little bit further, you might have a third type of grain structure. So, this distance from the surface might influence the rate of cooling at a particular point inside the material, and that will influence the type of grains which are formed, or the size of grains which are formed in a metal structure. Now, let us look at the space lattice. So, what is it? It is the imaginary network of lines. You can see a lot of lines in these drawings on the screen, and also you see intersections of those lines. So, what we assume is that at every intersection of these lines there is an atom present. Okay. So, space lattice is the imaginary network of lines with atoms at intersections representing the arrangement of atoms. Okay. So, you can see here in this sketch here, you have a lot of these imaginary vertical and horizontal lines, and then you have all the intersection points. You have a circle which is drawn or a sphere which is drawn, and that indicates the atoms present. Now, so by definition, atoms, molecules of or ions arranged, this is or ions arranged in a repetitive 3D pattern in long range order, means larger distance covered. That is what is crystal structure. Now, you might have also heard the word amorphous materials, where the crystals are not very well defined for a larger volume. So, even though they are arranged, but in short range order, that is what is amorphous materials. Now, atomic arrangement depends also on the atomic size and the valency. Now, we will talk about this unit cell here. You have this representation of the space lattice on the top right diagram, and each cubical region, or what that each unit cell, it is not necessarily cubic, but each unit cell can be explained in terms of their dimension of each of the corners, each of the edges, and also the angle between those edges. So, the angle you can say alpha, beta and gamma, and the dimensions are A, B and C, as you see in this sketch here. So, this is essentially what is the building block for any metal which we talk. Now, how many types of space lattice are there or identified? There are about 14 types of them. You might have studied this earlier also. You can see all of them are shown here. More detail on this, these pictures I am taking from the internet, so that it is easy for you to visualize things in a more easy manner. So, you have triclinic, monoclinic, orthorhombic, rhombohedral, tetragonal, hexagonal and cubic or isotropic. Okay. And within this you have other subcategories, like in case of orthorhombic you have simple, base centered, face centered, body centered, like that. So, there are total 14 space lattice arrangements are possible, and in case of most of the metals, what we see is mainly not all these are observed in most metals. What we see mainly are face centered cubic, body centered cubic and hexagonal close packing. Okay. So, body centered cubic, face centered cubic and hexagonal close packing. These are the three lattice structures which we see in case of metals. Now, those two cubic and one hexagonal space lattice are found in most metals. I just discussed that from the previous slide. So, these are a little bit closer look at those lattice structures. So, let us look at the face centered cubic. So, you can see here over here. So, you can see for this cube there are 6 faces. So, one on one face, second face, third face, and similarly for the other 3 faces which you are not seeing here. So, that is shown on the second diagram. You can see this one and second face, and then this is the third face. So, if I am going to write here also, so for you to see, this is 1 and then let us say this is 2 and then let us say this is 3. So, this is 1, 2, 3 and the other sides which you are not able to see, 2, 3, then this can be 4 and then this is 5 and then this is 6th one here. So, there are say 6 faces for the cube, and each face has at the center of the face there is one atom. Now, in the case of body centered cubic, you can see this is the one atom which is present at the center of the cube, that is right at the center, and so that is this one here. Okay. So, I am going to call it 1. Okay. Now, it also has atoms on the corners, that is 1, 2, 3 if we call. So, that is 1, 2 and 3 and 4, 5, 6, 7, 4, 5, 6, 7, and then of course, there is a 8th one there which you do not see in the first image. So, this is how they are. Now, one thing to note here is only this number 1 atom is completely occupied within the body centered cubic structure, whereas I made a little mistake here. So, it is okay. I am going to call this one as 0, so that it need not be written again. The 0th one is at the center, and all others are in the corners. Okay. So, you can see that this 1, 2, 3, 4, 5, 6, 7 and 8. So, they are all not fully occupied by the same cube. Now, in case of HCP, again you have similar type, but it is not in the shape of a cube, but you have the section is like a hexagon in nature. So, next one. Now, there are two parameters which are very important when we talk about this lattice structure. One is coordination number and the other one is atomic packing efficiency, that we will talk in the next slide. So, this slide let us focus on coordination number. It is also known as ligancy, whereas each ligands are atoms that are bonded to the central atom. Okay. So, that is how it is counted, the coordination number is counted. So, what is coordination number? It is the number of nearest neighbors for a central atom. Okay. Now, for case of FCC, that is the first one here, this one here, for the case of FCC, this coordination number is 12. How do we calculate that, or how do we get that number? So, as you can see here, if this portion here is the FCC structure and this is continuing, the remaining on the right side, this is like continuing the next unit cell. Okay. So, if this is the one of the unit cell, I can say one, if this is the central atom which I am considering, that central atom has these 4, 1, 2, 3, 4, these 4, that is 4 here, and then this, this, this and this, that is another 4, that is another 4, and then these 4 plus 4, that is equal to 12. So, it has 12 nearest neighbors. So, okay. So, that is what is coordination number for FCC is 12, that is how we get that. Now, for BCC, you can say similar way, you can for this as a center atom, if I am considering, I have these 4 and then I have these 4, that is 4 plus 4 is equal to 8. Okay. That is the coordination number for BCC structure, and if you take HCP structure, the coordination number is going to be, let us say if you consider this as a central atom, okay, that will have another 6 atoms on the other side, and that will again form 12. Okay. So, this is how the coordination number is calculated. Now, if you look at the atomic packing factor for lattice structure, so this is dependent on the equivalent number of atoms associated with each unit cell and atomic radius. So, you can see here FCC, for FCC it is 0.74, for HCP also it is 0.74, and BCC it is 0.68. So, if you look in the previous slide, for FCC and HCP, these numbers are also similar, just look at. Okay. Now, here again the picture on the bottom left, if you see, you can see that all the atoms are not completely occupied by one unit cell, some of them are also shared by the adjacent unit cell. So, on 6 faces, half of the atoms are shared, and on 8 corners, that means 1/8 of that particular atom on every corner is shared by unit cell. Now, then what you do is you calculate kind of the total volume of the unit cell and the volume of the atom, the share of the atom within that unit cell. Okay. So, if you total so then when you divide that volume of atoms in the unit cell and the volume of the unit cell, if you divide that by knowing what type of the atom, so you know the radius of each, you know what is this distance here, and you know what is this distance also. So, if you know the radius of both these, then you can calculate this atomic packing factor, and this atomic packing factor is actually related to the density, etc., are actually based on, or can be related to the atomic packing factor. So, you can look at this, you can pause for a minute and then go through these calculations, and then understand it better. And if you have any doubts, we can definitely talk about this in the review session.